Hello everyone, I am Shobham De, teaching assistant, advanced electrical machine design. So today, in the first session of the FEM simulation of motor, we'll see that how to start or initiate a project in ANSYS Electronics Desktop. So first you have to open the ANSYS Electronics Desktop software. You will find this kind of uh, window or page on your computer, and here just make sure that these tabs: desktop, view, simulation and automation. Under that, go to desktop and you will find this many options. There is a solver, it is here. So for any electromagnetic simulation and specifically for uh, motor simulation, we have to go to Maxwell. Click here. We'll do a 2D analysis, 2D electromagnetic analysis. So click on Maxwell 2D. So one Maxwell 2D uh, worksheet has been open. Now, first thing what you need to do, that is here under project 1, you can see the name is Maxwell 2D Design 3, and within bracket it is written as magnetostatic. So it will solve the magnetostatic problem. That means the all the geometries are static and there will be no effect of motion. So for our case, it's a motor, so the rotor will rotate. So you have to change the solver from magnetostatic to transient. For that, go to here Maxwell 2D, click on it, then solution type. Here, change the magnetic part from magnetostatic to transient. Click OK. You can see here that it has been changed from magnetostatic to transient. Now, today Uh, we will not discuss anything regarding drawing, that how to draw. Actually, there are three main parts of particular motor simulation in FEM. First one is the drawing of that particular geometry, then making it suitable for simulation, and then uh, getting the results and post-processing of the result. So the first thing is drawing. We will use today the user-defined primitives that is already loaded um, in the software. This is the by default given in the software. We will just change the various dimensions and get our geometry. But we will not learn today that how to draw a user-defined, maybe better to say your own geometry, but use the templates given here. And we learn that how to set up a uh, simulation, particularly for an interior permanent magnet synchronous machine. So for that, first we will go to draw, click on draw, user defined primitive, RMX part. Now we will first draw the stator. For that, go to slot code. You can see there are many options. So these many user defined primitives are there loaded. The thing is, I will show you the one uh, and show you that how to use them. You have to explore the software because the software is vast, so it is not possible to cover all of the things. I may be covering 1% of it, but you have to explore the others. So I am using slot code to prepare the stator geometry. So click on slot code. The window will come here. Now, what are the various attributes there? You can see various attributes are here. So I will recommend enlarge the window, especially the rightmost column. Here the description is given that what the various attributes are. Okay. Okay. So see here the dia gap means it's here gap means the air gap. So for an inner rotor machine, and we are drawing now the stator for an inner rotor machine. So dia gap means the inner diameter, that is the bore diameter of the stator. Now you can see here that various values are already uh, loaded here. So one thing I will tell you that from the first day only, you put not the values, direct values here, but put some variables so that you can change those variable on the way if required. So here in diagram, that is the bore diameter, we'll write simply D. Press enter. You can see that one add variable dialog box has been opened. So you have to define what is D. So the name is D, unit type is length, unit is millimeter. And now we are putting the value, what is the stator bore diameter. So for this design, we are choosing as 96. So all these attributes I will send you via Moodle. So you can see that diagram is D now and the value is 96. The reason behind it that you do not have to open these dialog box every time to change some attributes. It is just a variable, so you can change directly by changing the value of the variable. And also after that, if you want to make some sweep, that is the parametric sweep or something this kind of, so uh, it is a must to define some variable. So that is why I have started from now only to defining variable. Now the dia yoke means the outer dia of the stator. So I am putting here TO, enter, and the length I am giving as 160. Okay. Now for a 2D simulation, always put this length as 0. This length means the stack length. So put it as 0. And number of slot, QS, and I am giving it as 36. Slot type. So depending on the type of slot, the geometry of the slot changes. That is the shape of the slot changes. So you can see that for these user defined primitive, uh, there are slot type from 1 to 6. Okay, so I will choose here slot type 2. But what are the different slot types? You should explore on your own. Now, HS0, I think in one of your slide, I already have defined most probably in stator design that what are these things, HS0, HS1, HS2, particularly for a given slot. We are now uh, making a geometry of that particular type only. So you can refer to that. And also I will provide you the what is the geometry and what are the various attributes after this video, and I will upload it on the Moodle. So for now, just put here H is 0 and the yeah, value is 1 millimeter. Always put H is 01 as 0 because it is actually for the closed slot. You can see here closed slot, closed bridge height. So we are now making an open slot configuration. Now HS1, HS1 is also 1 here. HS2, HS2 is 14 millimeter. BS0, BS0 is the slot opening. and 1 millimeter length. BS1 4.7, BS2 is 7, and nothing else. This seg angle is the segmentation angle, so make it 0. So make it 0 to make the geometry continuous, otherwise it will be a segmented kind of thing. And length of region is 0. Press OK. So this is the stator geometry created. Now first thing to do to rename this one, the geometry as stator. Okay. Now we'll make the rotor. Go here in draw again. Use a different primitive RMX part. Now we'll choose the IPM code wizard. Click here. One dialog box will open. Now particularly in this first session, we'll um, use a V-type IPM geometry. Now here the diagram is, as it is an inner rotor machine, you could understand that the outer dia of the rotor will be at the vicinity of the air gap. So dia gap means that one. That means here the dia gap will be the bore dia, that is the inner diameter of the stator, minus 2 times the air gap length. So if I consider now air gap length of 0.7 millimeter, and I have already chosen the bore dia as 96 millimeter. So the dia gap for the rotor will be 94.6 millimeter. That is 96 minus 2 times 0.7. So I am giving it as dr, enter. So 94.6. Okay. Now dia yoke of the stator. That means for an inner rotor, dia yoke of the rotor for a inner rotor machine would be the shaft diameter. So I'm putting a ds, and the shaft diameter for this design is 45 millimeter. Length is again 0, as it is a 2D design. Number of poles, it is P, enter. So 8 number of poles we are choosing now. Pole type is 5. So again I'll tell you that like type of slot here in these user defined primitive. Pole type can be varied from 1 to 6. These are different types of pole. You should explore on your own that what are the differences in these types and what you can get by changing these geometries. Now D1, I will explain what is D1 while I will like pictorially I will explain that what is D1, and I will upload it to the Moodle. For this time being, put the D1 as um, just a value D1, enter, and it would be 92.6. Now, these are various dimensions of that particular geometry, which is concentrated on these type of, that is the pole type 5 only. So blindly just I am uh, giving you these dimensions, and I will show what these actual values are in a a particular image file so that you can relate to it. So now one I am giving as one is O2. Mhm. Now, Dimin Mag, sometimes it is required, but for this timing it is not required. It actually means the minimum distance between the two magnet segments, as it is a V-shaped magnet. So there will be two magnet segments per pole. That is, Dimin Mag defines the minimum distance between them. So, like if you put some minimum distance, so whatever be the situation, it will always maintain that distance. So there is no restrictions for this design. So we are keeping it zero. Thick magnets is the thickness of a particular magnet. Maybe now one thing to tell, as it is a V-shaped magnet, V-shaped IPM. So the combined length of the each leg of the V will be the total magnet length. So there will be two parts. One part will be the left side of the V, one part will be the right side of the V, magnet part. The combined length you have to put here. That is the magnet length. This is the thing that it may happen to you also. That means that somewhere whatever value I have put, there some mismatch is there, so that the geometry cannot be created. It is getting invalid. So you have to do it again. So actually, what I have done, I have already defined all the variables. What I have wrongly put, that is the B1 actually. If I change the B1 here, you can see there is the properties and all the variables which we have defined on the fly, that is reflected here. Now you put again draw user defined primitive RMS part and IPM code, put all the values, like dia gap would be dr, dia yok would be ds, length is 0, poles is p, pole type 5, d1 is d1, o1 is o1, like that. Put all the things. You can see a geometry has been created. Now, this is the core geometry, that is the iron part of the rotor. Now, in these slots, there will be magnets. To do that, first rename it from IPM code 1 to rotor. Enter. Now, copy the rotor, Control C and Control V. Double click on user defined, create user defined primitive. Then in the info code, see here, so 0 is core, 1 is magnets, 2 is duct, 3 one pole magnet, 100 is region. So we need now magnets. So just make this in info code to 1. Okay. See, the magnets has been placed on the position. Now the other part of the machine is the coils. For this, go here to draw user defined primitive, RM expert, lap coil. Now it is will place the winding in stator, so the attributes will be synchronous, will be in synchronism with the stator. So diagap here is D, diac is DO, length is 0, slots is QS, slot type is 2, HS0, HS1, HS2, ES0, ES1, ES2, RS is 0. Fillet type 0 layer. Yes, it is a double layer winding, 36 slot 8-pole distributed winding, so it would be a double layer one. Coil pitch 4. It okay, I'll tell you. First, make this 0 end extension, span extension. It is required actually for 3D model, actually for end winding. So currently make it 0. Seg angle is 0, limb region 0. Now the thing is, this coil pitch will not affect to make the geometry. First make it, is it okay? So you can see that coils are placed. Now again go here and do this, that coil pitch to 1. Coil pitch to 1 means one slot. If you do it, it would be a concentrated winding. Make it okay. See, it is now a concentrated winding. Now more than 1, any value more than 1 will make it a distributed winding. Coil pitch. Suppose I have put in 2. Okay. So it's a distributed winding. Okay. No. COIL. Okay. Now our all geometries has been created. Now what we have to do, that is um, see, it is a 36 slot 8-pole machine, so its HCF would be 4. So it has a symmetry of 4th, that is 1/4 symmetry is there. Now I want a configuration where two V shapes will be there in 1/4. So I will actually rotate. Um, I'll actually rotate this one, the rotor. This is for my convenience only, absolutely not related to the simulation. So I will select PM and rotor. Apply here this rotate tool. Click here rotate, and I will rotate it by, if you put here positive value, it will rotate anti-clockwise. And to rotate clockwise, you have to put the negative value. So I'm putting here is minus 22.5 degree. Okay. Okay. So, first quadrant, that is the 1/4, two magnets has come. Okay. Okay. Now, I will take only the 1/4 which is shown in the this quadrant, it's the first quadrant. So to do it, first select all the geometries, Control A, go to split here, click. Now, split means it will always split the geometry in two halves along a particular plane. The plane is here selected as YZ. You can see this is X, this is Y, and the Z is the positive Z will be coming from the screen, and we are now taking the YZ plane. So the direction of that plane would be the positive x-axis, and it is shown here by this arrow also uh, that this portion will be kept. Now you can see here in this window, keep result positive side. So the right hand half side will be kept, and split selected objects using whatever. So split all selected objects and the delete invalid objects. So it will delete the left hand side portion. Click OK. Again, go to split. We need now the upper half. So we'll change the plane to ZX. Click OK. So this is now our required geometry. Fit all. So the geometry is created. Now, um, we have to see here that if we click on PM, all the four PM parts of the two poles are getting selected. Okay, so one thing to notice here, that here the two magnets are actually joined. The reason behind that is we have not considered, let me show you, we have not considered the dimming mag. We have kept it as 0. Suppose we are making it 1, maybe D MPM, Dmin PM. So suppose it is 1 millimeter. Let's see what happened. And apply here. You can see the all the magnets has been shifted. So actually this distance has now become 1 millimeter. But the magnet is now not in synchronism with the core. So we have to change the core also. So rotor, create user defined primitive. So that dmin mag, which we previously put at 0, DMPM is okay. Now it is good. So while clicking on the PM, all the four segments are getting selected. So to uh, make them detached, click on it, right click on PM, then edit, Boolean, separate bodies. Then you can see that four PM segments are created. Okay. So before doing that, so we have to do it for coil also. that because all the coil segments are united now. So before doing that, we will assign the material for stator and rotor from here, properties, edit. First, you have to check whether these two things, these two libraries, show project definitions, select all libraries. Both of these should be checked. After that, search here, maybe M19, yes, M19 24G, I'm selecting. There are many other materials are there that you should explore further. Okay, I am telling you right now only. So maybe it is M235. See, there are ArcelorMittal, Cogen Power, and various company materials are there. Like this, there are various materials from specific companies are there, but those are available only the original version, which is one of which is provided by IIT Bombay, is available. Otherwise, in the student version, those will not be available. So I am using a library version that is not given by any company. That is one, that is M1924G. It's okay. So uh, under these M1924G, rotor and stator heads have come. Now take the PM, edit. So I will take in 35. See, only the Arnold magnetics. So these are only there. Okay. So I will take this one, permanent magnet in 35. Neodymium magnet 35. It's okay. Now coil, it would be copper. So edit. See, copper system material. It's fine. Okay. Now here under this coil and under copper, on the coil, click here, right click, edit, boolean, separate bodies. Right, write the exact thing what we did for magnets. Click here. See, all the coils has been created. Right click on copper, collapse all. Okay, so these are the separate coil parts. Now the winding configuration you have to determine previously is a um, 36 slot 8 pole um, machine configuration. So and three phase machine. So for that thing, how the ABC phase will be distributed, that you have to determine previously, and then you have to apply it here. So first I will name these windings. So as I know that for this configuration, which one will be A phase. So you have to know it. So I am doing that. Selecting all those which are of which will be of A phase. A, this C, this B, this will be again A. Okay. And come here in the properties, click. This will be A. Enter. See, all these things as named as A. Now after that A, this will be C. Here from here it will be B. We will rename it as B, and the rest of them will be C. Okay. For your convenience, you can color them in different colors also, maybe RYB. This would be Y, B. We can now see the three phases. Red is A, yellow is B, and blue is C. Okay. Now you have to assign them coil. So for that, you have to I will select first the positive ones. So suppose this A is positive, then it is minus C, then it will be plus B, then again minus A, then again plus C. You can do one by one, but I will recommend that you will select first all the positive coils, then right click here, then assign excitation coil. If you click here, there is no need to change the base name. The number of conductors, what will be the number of conductors per geometry? That is in here for but one layer of a slot, that is for a one rectangle in a slot, how many number of conductors will be there? That is uh, the turns per coil. Suppose I am writing is at T of C, and this the polarity will be positive. Okay. Now it will ask you what is TC. Suppose it is 1. Okay. Now select the negative ones. So this will be minus C, then plus B, then it is minus A, then it is plus C, which will be minus B. Right click, assign excitation, coil. So it will be TC only, and polarity will be negative. Okay. Now all this assignment has come here. Okay. Under excitation, you can see all these assignments has come. Now click on excitation, right click, add winding. Here you can assign the phase A. Phase A. Let's make it stranded. Okay. Right click on phase A, which has been created now. Add coils. All the A terminals. Okay. Now if you click on this phase A, you can see uh, these terminals are showing. So that means actually it is not required that from where the winding is coming and where it is going. It is not required to define in a 2D simulation. It is not needed for electromagnetic analysis. What is only needed that which polarity of the winding is of a particular winding, suppose this one, which polarity of that winding is, how many conductors are there in one single this geometry, and how many that particularly which geometries are in series with others. Suppose these six are in series. That means from these three, winding is going to these three. That means whatever current here, suppose I am pushing here A sine omega t plus maybe 120 degrees, suppose. Then here also, at that particular instant, here also A sine omega t plus 120 degree will flow. And that is defined by this grouping. In phase A, all these conductors are there. Okay. Similarly, I have to create phase 2. So add winding again, which is phase A and this phase B, stranded. Okay. Right click, add currents, all the B. Okay. Click on it. See the phase B is there. Are selected. Now right click on excitation. Add phase C. Stranded. Okay. Right click. Add curves. All the phase C's information. Okay. So this is phase C. Now the winding assignment is done. Now we have to do the this one. That is the I have to assign the polarity of the permanent magnets. So to do it, I have to select. Suppose I am coloring the north whole polarity magnets as red. It's okay. And the south ones is blue. Okay. So to me, the north means uh, the north will be the at the air gap side, and the south means north will be at the shaft side. So to assign the polarity, first from here select uh, change the selection from object to face. Click here on the particular magnet, modeler, coordinate system, create faces means face coordinate system. Click here, now come here. It will snip. I think you should zoom a bit. I think I should zoom a bit. So you have selected the face already. Modeler, coordinate system, create faces. Snip here that one corner of the magnet. First click here, then go to the other end, click here. See the x-axis is now towards the air gap. So that means the direction of the this particular magnet will be towards the air gap, but this has not been assigned yet. I will assign it. Before that, select here on the other magnet, modeler, coordinate system, create faces from here to here. Similarly for the other two magnets also, modeler, coordinate system, create faces. It's from the opposite side, here to here. So X is inward now, as it is. I intend to assign it as a south. Modeler, coordinate system, create faces here to here. Okay. Now, under coordinate system tab, you can see there are four faces and one global. Global means, if I select global, global means this one. That is the global coordinate system. Now, change the selection from face to object again and select on a particular magnet segment, come here to the properties, orientation from global to facies 1. Now the orientation of the magnet has been changed. Do the same for other segments, global to facies 2. This is 1, global to facies 3. It's another one, and global to facies 4. Okay. So you could understand that not only the simulation time, but this processing time will also be reduced if you reduce the geometry. So if it is a full geometry, same thing we'll have to do for it, uh, maybe 3 more times. Okay, as well as like the what is the windings. So now all the assignments has been done. Now one thing we have to ensure that which part of these geometries will rotate. For that thing, we have to create a bend. Now, how to do it? First, I will take a straight line from here. First point is this one, that is uh, origin. Second point is anything. Okay. Make sure that here, like here, you can see the coordinates. Okay. Make sure that y is 0 while you are choosing the second point. Click here. Now you can see that one polyline 1 is created. Double click, sorry, click on the plus sign beside the create polyline, then double click on create line. So we want the length of the straight line to be just uh, in between the air gap. Okay, double click on the create line. So our um, bore dia, that is the stator inner dia, is D. So the length, that is the point 2, will be D by 2, and our air gap length is 0.7. So we can take minus 0.5. Okay, 1 second. Yeah, minus 0.5. We have to specify the milliliter here. Okay, now we can see the straight line is here, ended here. So it is actually the our board dia D, and in radius sense it is D by 2, and here it is D by 2 minus the LG, that is air gap, that is 0.7, but we have put it minus 0.5. That means these distances from the rotor to the end of this line is 0.2 millimeter. Now we'll make it fit all first, then select the polyline 1 and sweep it. This is the option, sweep around axis. Click here and sweep it for 45 degree. Make the round to natural. Okay. Oh, sorry. I have to do it for 90 degree. Okay, make it 90. Okay. Okay. So one geometry has been created which covers all the rotating parts of the machine. Okay. So this will rename as band. Okay. Now we will assign the motion here. Select the band, right click, assign band. Now our motion will be rotary motion. Click on rotation, data. Initially don't give anything, but I will suggest for this time being, make it as gamma, Gamma. Gamma. Okay, enter. So gamma angle degree, make it 0. Oh, it will be needed afterwards, I will say. Okay. One more thing. See, it is in the model, motion setter double click data, it is gamma, the mechanical RPM, which will be the synchronous speed, NS, enter, angular speed RPM is a 3000 RPM. Okay, so you can see here, data is gamma, mechanical NS is 3000 RPM already defined. Okay. So if we click on the model, sorry, motion setup one, you can see the shaded region is only the band you have created now, and under that part, all the rotary part is covered. Now we have to make boundary. So the boundary there are for a reduced model, as it is a 1/4 model. The there are three kinds of boundary. One is the matching boundary, and another one is the vector potential boundary. The vector potential boundary is outside that boundary, that it takes that there is no flux will go, and all the flux, whatever the magnetic calculation, electromagnetic calculation, will be confined with that particular geometry. So to make that boundary, we will again take a straight line here from origin to any length, right click, done. So here is the polyline, create the create line. Then the radius will be, here it will be outer the DO by 2, maybe plus 1 millimeter, plus 1 millimeter. Okay. So you can see this polyline has been created. Okay. Now rename it. Okay. Before renaming it, select the polyline 1 and again sweep around axis for 90 degree. Make it to natural. Okay. So this geometry has been created. Rename it to region. Okay. Now we have to um, make the first the matching boundary. So master and it was previously called master and slave. Now it is called as matching boundary. So change this object selection from object to edge. Select the edge. See, it is showing the region edge. Click here. The edge is selected. Right click. Assign boundary. It is a previous version. It is a 2022 version. Sorry, 2020 version. In the newer versions, you will get matching. Okay. Under that, you can get independent and dependent. Before 2021, it was given as master and slave. So while I am clicking on master, you should click on matching, then independent. So master. So you can see one vector direction is shown here. It is outward. Keep it as it is. Okay. Then go to the other part here. Select region edge, this one. Select, right click, assign boundary. This will be slave. For you who are using the version uh, 2021 onwards, you should click on matching, then dependent. So the master boundary, you, it would be master one, which I have created now. Now see, It is the vector is on reverse direction. Okay, I am doing again to give you clarity. So here region H, click, right click, assign boundary. So okay, see, uh, first make it master one. See, it is showing downward. Make it first reverse direction, so it would be upward. Now the thing is, that if there are two poles in your symmetric geometry, that means whatever the direction of V at the uh, master boundary would be the same at the slave boundary. If the uh, symmetric geometry contains odd number of poles, then the direction of B at the master boundary would be the opposite of that at the slave boundary. So here in our 1/4 model, that is a symmetric model, there are two complete poles. So that means whatever the direction of B at the master boundary will be same of the slave boundary. So the BS equals BM, that is B slave equals B master. It's okay. Now we have to assign the vector potential. Click this edge. It is showing a stator edge, so it is not. You should, yes, region edge. Click here, right click, assign boundary, vector potential, 0, 0 over per meter. Okay. Now return. So you can see here under boundaries is master 1, slave 1, vector potential 1. This thing has been made. Okay. So this was the content of the first class. So those who have not attended, please make sure you have covered all the things. And for all, whatever the geometries and the dimensions I will upload on Moodle, you have to draw it and do all these things. Whatever the preparations I have done here, you have to do all these things and come to the second class, second class of APM. Okay, so I'll save it. Okay, so save it at your some suitable place, but make sure that there will be enough space, because upon simulation it will create a lot of result file of large size. Okay, so do all the rest of the things and we'll meet on the next APM class. Thank you.